The next example that we want to look at asks us to compute the length of the curve x equals y squared over 4 minus 1/2 log absolute value of y for y values between 1 and e. Now this looks a little bit different than we're used to. I mean, this, instead of asking us for the arc length of a curve y equals something in terms of x, we have the opposite happening. X is something in terms of y. And we have a couple of ways of maybe thinking about this. One would be we can just use the normal theorem that we're used to, or the definition, which says if we have some continuously differentiable function on some interval, arc length is defined to be this thing. And there's nothing special about the letter x here. We're not revolving anything about an x or a y-axis, and so this x is really just whatever variable you want it to be. In the case of example 3, we use the variable t. So here for this problem, we could just think about this as, instead of the letter x, let's use the letter y. And we could apply the usual process for computing arc length. Another way of thinking about it, and perhaps a way that's a little bit more geometrically appealing, would be we know that arc length, or sort of our heuristic argument for arc length, asked us to compute the integral of the square root of dx squared plus dy squared. And we chose to factor out a dx squared, but instead we could certainly factor out a dy squared. And what that would look like would be the square root of dx dy squared plus 1 dy. And so here we can apply the same process. We have some ability to take dx dy. And so we can do that, and we can integrate this thing. And once we've done that, we'll have the arc length of the curve. So in fact, that is what I want to set up here. And I want to think about what is dx dy in this case. So the derivative of x with respect to y, I can apply my power rule for the first term. That's going to be y over 2. For the second term, the 1/2 sticks around, and I know the derivative of natural log of absolute value y is 1 over y. Fairly straightforward computation for dx dy. I know that I am working with x values between 1 and e, and so what I want to integrate here is the square root of dx dy squared, so y over 2 minus 1 over 2y squared plus 1. Now if you spend some time staring at that, it's going to be pretty hard to come up with a u substitution that is going to make this integrable. So since our only options for actually integrating things right now are u substitution and inspection, we had better hope that this is going to be integrable by inspection. And really by inspection, what I mean is first do some arithmetic, then inspect it and do an integral. So we really want to simplify that integrand first and see if we can make it come out to be something that looks a little bit nicer. So let's do that first by expanding out the term y over 2 minus 1 over 2y squared. So I know that in order to expand this, I'm going to have the first term being y squared over 4. The second term is going to be minus 2 times the product y over 2 times 1 over 2y. And the last term is going to be plus 1 over 2y squared, which I suppose we can write as 1 over 4y squared. We still have that plus 1 floating around, so let's keep that. And next what we want to do, so let's see, 1 to e square root, we have a y squared over 4 still. Notice that the middle term, the y's cancel, and I'm left with 2 over 4, which is the same as 1 over 2, so I have a minus 1/2 for that middle term. We still have a plus 1 over 4y squared, plus 1 dy. Continuing to simplify, 1 to e square root of y squared over 4. The minus 1/2 and the plus 1 work together to give me a plus 1/2. Plus 1 over 4y squared. Yep, that's it for the things inside the square root. And now what we notice is that this is very similar to what we just were looking at, this term here. Maybe I'll actually box those to sort of emphasize the similarity. The difference is that instead of a plus 1/2, I had a minus 1/2 earlier. And the way we can, we notice then that what I've boxed here on the right in red will factor as the square of two terms, as the square of something. In other words, it factors as integral from 1 to e square root of y over 2 plus 1 over 2y squared. And let's make that square root appropriately sized. Great. So maybe the observation that I'm making here is, so remember when we're kind of, actually maybe I'll write this out in a little bit more detail. Let's do some side work. Remember that a plus b squared is a squared plus 2ab plus b squared, and a minus b squared is a squared minus 2ab plus b squared. So the only difference between the square formulas here are whether or not I have a plus or a minus on that middle term. And that's the observation that I made with these two red boxes. This first red box has a minus on the middle term, and the second red box has a plus on the middle term. But I know the first red box factors as something squared. It was this y over 2 minus 1 over 2y squared. And so that tells me that the second red box, where the only difference is the plus 1/2 instead of the minus 1/2, is going to factor as the same thing, but with a plus in the middle. So here I have now the square root of this thing squared, and lo and behold, the square root and the squared cancel out, and this is the integral from 1 to e of y over 2 plus 1 over 2y. And this is a thing that we can actually integrate. So this is equal to, let's see, the integral of y over 2 is y squared over 4. The integral of 1 over 2y is 1/2 natural log of the absolute value of y. And we're evaluating from 1 to e. Great, so we can now evaluate at e. We're going to get e squared over 4. Natural log of e is 1, so that's e squared over 4 plus 1/2. If we evaluate at 1 now, we're going to get 1 over 4. Natural log of 1 is 0, so that's it for this term. And then finally, simplifying a little bit, we get e squared over 4 minus 1 over 4 plus 1 over 4. Great, so we were able to compute the length of this curve. So that's pretty nice, and I think that's the last arc length example that we're going to have here. One little piece of trivia for this sort of question was that in order to compute, or in order to create a function which had this nice property where once I squared it and then added 1, I got something else squared, I was taking advantage of something called a Pythagorean triple, which is, you can think about geometrically as a right triangle with sides whose lengths are all integers. So for instance, a 3, 4, 5 right triangle has lengths integers. And there's a nice sort of way that you can create lots of those triangles. And I was taking advantage of the method of creation there in order to create a function that had this property. So that was kind of a fun thing to work out. But right now, our lack of integration techniques is really making a lot of these problems difficult because we don't really have a lot of ability to integrate weird functions right now. So we'll get that as we do chapter 3, but for the moment we are confined to doing some examples that are constructed very specifically to work out nicely, kind of like this one was.